Welcome back to Bite-Sized Breakthroughs, where we break down complex research into bite-sized chunks. Today we're diving into a truly intriguing paper titled The Case for Learned Index Structures. Dr. Paige Turner, a leading expert in this field, joins us to unpack this groundbreaking research. Paige, can you give us a high-level overview of the paper's main focus?
Thanks, Alex. This paper tackles a core challenge in database systems: how to efficiently access data. Traditional indexes like B-trees, hash indexes, and Bloom filters are widely used, but they have inherent limitations. They're designed to be general purpose, so they don't fully leverage the specific data distributions often found in real-world datasets. This can lead to inefficient storage and slower lookup times. The paper proposes a revolutionary solution, replacing these traditional indexes with machine learning models, specifically deep learning models, which they call learned indexes.
That's fascinating, Paige. So these learned indexes essentially learn the underlying structure of the data and use that knowledge to optimize data access. Can you explain how that works in practice?
Absolutely. Imagine a B-tree index. It's essentially a model that maps a key to the location of a record within a sorted array. The paper argues that we can replace this model with more sophisticated machine learning models, like neural networks. These models can learn complex data distributions, effectively predicting the location of records even faster and using significantly less memory. It's like training a model to understand the data's natural order and leverage that knowledge for faster and more efficient access.
That sounds promising, Paige. But how can we be sure that these machine learning models won't introduce new complexities or errors? After all, traditional indexes offer certain guarantees that machine learning models might not.
That's a valid concern, Alex. The authors acknowledge that learned indexes might not provide the same strict semantic guarantees as traditional structures, but they argue that the potential benefits outweigh these limitations. They specifically address this challenge by developing a framework called the Recursive Model Index, or RMI. It uses a hierarchy of models where each model specializes in a specific range of keys. This approach helps to address the accuracy limitations of single models, ensuring that the final prediction is sufficiently precise.
The RMI framework is intriguing, Paige. Can you elaborate on its specific structure and how it works?
Sure. Think of it as a series of stages. The top-level model is designed to learn the overall shape of the data distribution, providing a rough estimate of the record's position. As you move down the hierarchy, each subsequent stage refines the prediction, focusing on a smaller range of keys. This multi-stage approach allows for more complex models, which are better at learning the overall patterns while also ensuring high accuracy at the individual instance level.
So the RMI essentially breaks down the complexity of the data distribution into smaller, more manageable chunks, allowing for more accurate predictions with less computational overhead. That's a clever solution.
Exactly, Alex. And the beauty of this approach is that it allows for the combination of different model types, like neural networks and traditional B-trees, to achieve a balance between performance and accuracy. They call this hybrid indexing, where the system dynamically chooses the best approach based on the data distribution and the desired level of precision.
This is starting to feel like a real paradigm shift in indexing, Paige. It's not just about tweaking existing methods, but proposing entirely new ways of thinking about data access. Let's delve deeper into the paper's experimental findings. What specific datasets did they use to evaluate these learned indexes?
They tested their learned indexes on a variety of real-world and synthetic datasets. One of the real-world datasets was a collection of 200 million web server log entries, containing timestamps for every request to a university website over several years. This dataset presented a challenging scenario for the learned indexes, as it contained complex temporal patterns due to various factors like class schedules, weekends, holidays, and department events. They also used a dataset of 200 million map features with longitudes, which was relatively more linear. Finally, they generated a synthetic dataset of 190 million unique values sampled from a log normal distribution, which introduced a highly nonlinear data distribution.
So they covered a good range of data distributions, from highly irregular to relatively linear. What were the key results of their experiments?
The results were incredibly promising. Across these diverse data sets, the learned indexes consistently outperformed cache optimized B trees in terms of both speed and memory usage. For range indexes, using the RMI architecture, they achieved speedups of up to 1.5 to 3 times faster and reduced memory usage by up to 2 orders of magnitude. This is a significant improvement, particularly considering the B trees were already highly optimized for cache efficiency.
Wow, Paige, those are impressive numbers. It sounds like learned indexes are not just slightly better, they're demonstrably superior in terms of performance and storage efficiency. What other types of index structures did they explore using machine learning?
They also explored learned point indexes, which focus on optimizing data access for specific keys, and learned existence indexes, which aim to efficiently determine if a key exists within a dataset. For point indexes, they created a learned hash function that significantly reduced the number of conflicts in hash maps, improving storage efficiency and potentially leading to faster lookup times. They achieved up to a 77% reduction in the conflict rate, which can have a huge impact on performance, especially in distributed systems where communication overheads can be significant. For existence indexes, they demonstrated that learned Bloom filters can significantly reduce memory usage compared to traditional Bloom filters, while still maintaining the property of no false negatives.
That's a comprehensive set of findings, Paige. It's clear that learned indexes hold tremendous potential to revolutionize indexing in database systems. But let's hear from Professor Wide Spectrum, a leading authority on database systems, to get his perspective on this research. Professor Spectrum, what are your thoughts on the paper's key contributions and innovations?
Alex, this paper is a real game changer. It's not just about incremental improvements to existing indexing techniques, it's about fundamentally shifting how we think about data access. The authors have successfully shown that we can replace traditional index structures with powerful machine learning models. The Recursive Model Index architecture, in particular, is a brilliant solution to overcome the accuracy limitations of single models. They've also demonstrated that these learned indexes can outperform traditional structures in terms of both speed and memory usage across a wide range of datasets. This research has the potential to significantly impact the future of database design and implementation.
I agree, Prof. Spectrum. It's a compelling case for a paradigm shift in indexing. Paige, can you elaborate on any specific examples of the improvements they achieved with learned indexes?
Sure. One of the most striking examples was their experiment with a dataset of 200 million web server log entries. Using a learned range index, they achieved a 70% speedup compared to a cache-optimized B tree while using significantly less memory, about an order of magnitude smaller. This shows that learned indexes can be particularly effective for datasets with complex data distributions, which are often challenging for traditional indexes to handle efficiently.
That's a substantial improvement, Paige. And as Prof. Spectrum mentioned, this research holds the potential for significant impact. What are some of the potential applications and broader implications of these findings?
The potential applications are vast, Alex. Learned indexes can be used to enhance the performance of various database systems, including analytical databases, in-memory databases, cloud-based databases, and search engines. For example, they could be used to accelerate queries in data warehouses, improve the efficiency of search engine indexing, and enhance the performance of fraud detection systems. The ability to efficiently handle massive data sets with complex data distributions is particularly valuable in today's data-driven world.
I can see how this technology could be transformative, Paige. Prof. Spectrum, you've mentioned the potential impact, but are there any challenges or limitations that we should be aware of?
Yes, Alex. While the paper presents a compelling case for learned indexes, it's important to acknowledge some of the challenges and limitations. The current approach primarily focuses on read-only workloads and requires further research to effectively handle write-heavy workloads like inserts and updates. Also, the paper mainly considers in-memory data structures, and additional research is needed to explore the application of learned indexes for disk-based systems, which often involve paging. Finally, training complex models can be time-consuming, and optimization techniques are needed to improve the training efficiency.
Those are valid concerns, Prof. Spectrum. Paige, do you have any further insights into these challenges and how the authors address them?
Yes, Alex. The authors recognize these challenges and outline several future research directions to address them. For example, they propose using delta indexes and online learning techniques to handle inserts and updates more efficiently. They also explore the potential of using models to learn page pointers to optimize data access in disk-based systems. The paper also acknowledges the need for further research to optimize the training process and explore the potential of different ML models like recurrent and convolutional neural networks for various indexing scenarios.
That's promising, Paige. It sounds like the authors are well aware of the challenges and are actively pursuing solutions. Prof. Spectrum, in your view, what are some of the most exciting future directions for this research?
I think the most exciting future direction is to extend the idea of learned indexes to handle multidimensional data. Machine learning models, particularly neural networks, are extremely good at capturing complex relationships in high-dimensional spaces. Imagine a model that could efficiently predict the location of records based on any combination of attributes, not just a single key. This would be a true breakthrough in data access and could have a profound impact on database systems.
That's a compelling vision, Prof. Spectrum. And with the emergence of specialized hardware accelerators like GPUs and TPUs, these models could be executed even faster and with less energy consumption. Paige, what are your final thoughts on this groundbreaking research?
This research has the potential to reshape the future of data management systems. By demonstrating that machine learning models can be effectively used as index structures, the authors have opened up a whole new avenue for optimizing data access. The findings are incredibly promising, suggesting significant performance gains and memory savings, particularly for datasets with complex data distributions. While there are challenges to overcome, the research offers a compelling vision for a more efficient and powerful approach to data management, especially with the growing adoption of specialized hardware accelerators. It's truly exciting to see how machine learning is being applied to solve fundamental problems in database systems.
Thank you both, Dr. Turner and Prof. Spectrum, for this in-depth discussion. It's clear that learned indexes are a game changer in data management, offering exciting potential for improved performance, efficiency, and scalability. We'll continue to follow the advancements in this field and keep you updated on the latest breakthroughs. Until next time, stay curious.